I mean, we can have it smaller, but we haven't talked about anything realistically yet. But for now, just to kind of give you guys some quick information, open it up all the way. And then your next critical thing that you're going to need to do is working distance. Working distance is very important as far as X-ray goes, because what you have is, you have an X-ray detector that's coming in, right? You have your sample stub that's here. Well, the electron beam is hitting the sample, and then X-rays are bombarding off. And if the sample is too low, X-rays will not hit the detector. If the sample is too high, X-rays will miss the detector. So there is working distance that's critical that you need, and that is 10 millimeters.
Max, min, or steady 10?
You can vary plus or minus 2 millimeters.
Okay.
But 10 is your ideal. And as you can see, I'm at 11.57 millimeters, right? So the plus or minus 2, right? And so if I come up here and if I focus this, just throw a little focus window up here. Let me just come up a little bit more. Let me just focus this guy a little bit. All right, anyway, pretty close. 11.63 millimeters. Okay, so I can be a little bit closer, but I'm getting good count rate to where it is right now, so it's okay. I don't have a major problem with it, so I'm okay with it. Just move this straight up a little bit. Okay. All right. So, working distance, right? And you read that over here, right? And you also read that over here, right? And when I change my focal plane, right, that changed the working distance. See how that changed the working distance? Right? But realistically, what I've done is I've taken the beam and I focused it a little bit lower. The sample is still out of focus because I would need to lower my sample down in Z now in order to accommodate that. Right? We're familiar with how we change the working distance? And then obviously I would use my focus window, and that helps you focus a lot quicker. Right? Right about there? Great. Okay. So again, roughly 11.83, which means stage says we're at 10, but realistically the focal plane is 11.83. So if we wanted to bring this up a little bit more, like the 10 millimeters, I would need to come over here and put 9, right? And that brought that up to, another millimeter up, open up my window, because that still hasn't changed, so I need to refocus, right? So if I refocus that, now that's changed to 10.58, right? So far so good, just working distance, right? So the microscope parameter is 20,000 volts of acceleration voltage, because that generates a lot more X-rays, right? And 10 millimeters working distance, but plus or minus 2 millimeters as far as that goes. Okay? All right. Now the microscope becomes a slave, and realistically, we don't use it anymore. Because we have this software bundle over here, which becomes very, very powerful now. All right, so that's the image that we see, and this is the way the software window opens. And so I want to go over something over here really quick. And see this preset here? That's 100. See what it says live time? See it says live time 0.0. See this number that's fluctuating 19, 20%. See this number that's fluctuating 5,000, right? So I'm going to collect the spectrum, just ignore what I'm doing right now. Okay. So basically right now, this preset 100 seconds live time, it's counting 5, 6, 7, 8, 9, 10. And it's going to count until it hits that preset, right? Because that's what you told it to do. I could always blue that preset out, and I could put 20 seconds there if I wanted. And then as soon as this hits 20 seconds, it'll stop accumulating X-ray information. Because that's what we're doing right now. We're accumulating X-ray information from everything that we see there. The detector is on, it's live. As long as we see a beam, it's going to have information. Okay? So, right now I hit 20, it stopped at 20. It hit the preset, so it stopped.
So what is the recommended amount of time? What the most accurate?
Minimum, I'm going to say 30 seconds.
30 seconds. Okay.
Is going to be your minimum. But I can't tell you what the recommended time is because I don't know what you're looking at. There's customers that run this for hours. There's customers that run it for 30 seconds. There's a big change here, right? If you're looking for trace elements like lower than like 1 ppm of something, be rest assured you're not going to see that in 30 seconds.
That's preset. 30 seconds is preset.
It's just a preset time. We can make this preset anything we want, right? I'm just going to set it as default for 100 seconds. That's what I'm going to set. But you can stop the acquisition anytime you realistically like. I could acquire a new spectrum, right? It's acquiring. See, it's counting. 1 second, 2 seconds, it's stop. It stopped after however long I hold it to, right? this traffic light becomes valid for whatever window I'm currently in. That's going to make sense in a second, but right now I don't want to get too confused here, right? So, for right now, all I want you to know is just preset, it's a lifetime acquisition, and I stopped it at 3.3 seconds. I've got 20% dead time, and it's fluctuating between 19, 20, 21, and it will run. It'll run according to what the beam of the microscope is doing. As long as the beam is on, right? If I turn this beam off, beam's off, look what happens here. No percentage of dead time, it's gone, right? If I try to acquire a new spectra, there is no spectra, because I have no beam, right? If I don't have a beam, I can't accumulate any data, right? It's counting, 5, 6, 7, 8, right? It's counting. But what is it accumulating? Nothing. There's no information there, right? So we need the microscope beam to be on in order for it to see information, right? Because without an electron beam, I have no X-rays. All right, back to what we were talking about a second ago. So this dead time, right? 21%. That means 21% of the X-ray events that are hitting that detector are not being processed.
And that's ideal number, or we want this close to 100?
It works like a traffic light. It goes green, yellow, red. Okay, but it is an ideal number because as soon as it's like 30 or 40%, it turns yellow. Then around 100%, it'll turn red. But because this pulse processor and this detector are manufactured the way they are, this number will be pretty much the same, unless we decide to open up some apertures on the SEM. Right? Like, I could simulate something slightly different right now, just to kind of go around. Okay. What I've done now is, I've pulled out your aperture rod, and I've given this a lot of beam. I've given it so much beam that we have 42,000 X-ray events per second, and this went to 79% dead time. So, the more beam, right, the more X-ray events, and basically at 79% dead time, it's saying that, hey, at this time constant, see this TC, this comes into effect now to this time constant, it's processing every X-ray event for 4 microseconds. So at 4 microseconds, it's saying, hang on a second, you're giving me a little bit too much information because I'm looking at this every 4 microseconds, and because of that, I'm processing, I don't know, 79% of the information is not being processed, I'm only processing 20% of that information. Right? So, time constant. So I could tell it, saying, you know what? I want you to process this information quicker. I don't want you to look at it for 4 microseconds. I want you to do it at 2 microseconds. So at 2 microseconds, look at it to my ratio. Because it's processing information quicker. It's saying, that's aluminum, instead of being like, I think that's aluminum, I'm pretty sure it's aluminum, yeah, it's aluminum, right? At 2 microseconds, it's like, aluminum, right? And I can even go faster. I can go to 1 microsecond. Now look what happens to my dead time. Right, it's going to get, and hang on a second, let me just see something here. I got to reduce that. That's pretty good, actually. Just going to stop. Let me change that to 0.5 microseconds. Let me go even faster. So look at 0.5 microseconds, what happened to my dead time. It's almost like non-existent. Right? So there's a ratio here. And the ratio is, and the reason we have these time constants, if you're processing information very, very quickly, the resolution gets poor. The peaks get a little bit wider, let's say. So you need to process information at a certain time constant for better resolution of that data. But if we're not looking at spectral peak resolution, we're not looking at the peak resolution, and if we're trying to acquire an X-ray map, which is pixel resolution, then we want a lot of X-ray counts. We want as many as we can get. We want those 40,000 counts. And we could run this at, let's say, time constant 1, picking up a lot of X-ray counts. So now, if I want to, let's say, okay, here's my peaks, and if I want to collect an X-ray map, I'm just going to skip for a second. If I want to collect an X-ray map, right, at this count rate, at 50,000 counts a second, my X-ray map is going to develop very, very quickly. So here's my SEM image, right? That's the image, right? Here's a grid. Well, guess what? The grid is copper. The background is aluminum. I've got some oxygen or a little bit of carbon, and gold is sputtered all over the whole thing. So this is developing an X-ray map. Right now, this X-ray map did one sweep at 50,000 counts a second, and it already gave me all of this information. It didn't give me just one little purple thing and it took 3 hours for this to develop like it does on old SCMs with the nitrogen detectors. This did one sweep and gave me all that X-ray